Okay, let's talk about derivatives. Last time, I indicated that derivative along with integration are two most fundamental concepts that motivated calculus. Derivative was motivated by the need to compute the slope of tangent line of a curve. Let's look at a curve and its tangent line and see how we can compute. Here we have a curve y equals fx. In order to compute the tangent line at point A, x equals a, y equals fa, we take a secant line instead of tangent line because we don't know the slope of tangent line. So we take a nearby point where x is x and the y coordinate will automatically be fx. So we have a point x comma fx and the original point, which is a comma fa. We connect those 2 points and we get the secant line. Let's compute the slope of the secant line. Well, by the well-known the formula for slope, you basically take how much y is increased divided by how much x is increased. In other words, we take fx minus fa divided by x minus a. And then as the secant line gets closer and closer to tangent line, in other words, as x moves close to a, the slope of this secant line will be getting closer and closer to the slope of the tangent line. Therefore, one would expect the limit as x approaches a of the slope should be equal to the slope of the tangent line. And that is exactly the definition of f prime at the point A. There is another definition which looks slightly different, but they are really the same. Let's try to compute f prime at x at a point x instead of point A. Why do we want to do that? Because we want to think about the derivative as a function rather than derivative at an isolated point A. So consider x being the variable that varies. We want to compute the f prime x for any x. If we apply the same formula as before, we run to the difficulty with the notation because x is now in the place where a was and we run out of notation. We have to use some other letter for x. What people usually do is to think about the following picture. So the original point is a, now we replace this by x, and the nearby point we denote this by x plus h, where h is how much x value changes. And as before, we have the point x plus h comma f x plus h. And therefore, we obtain the limit of the slope of the secant line, which is our derivative. So we have the following formula. F prime x is limit as h goes to 0, fx plus h minus fx divided by h. Both are definition of derivative. I would say if you want to compute f prime x for arbitrary x, use the second formula. If you want to compute f prime a for a fixed point, for example, f prime at 2, you can use the first one, or you can use the second one, it doesn't matter. Let's look at one example. Take the function fx equals to square root of x. We want to compute f prime x. We simply follow the definition here. I suggest that you copy the definition as your first step. So we simply copy the definition from above. F prime x is equal to limit h goes to 0, fx plus h minus fx divided by h. And then we simply substitute fx into the definition. We got the following. Square root of x plus h minus square root of x divided by h. Now the question is how to compute this limit. Well, in my previous talk, I indicated one out of the several techniques that I mentioned, and one involves with the square root of something. And here we have a square root of this expression here. What we do is to multiply top and bottom by the conjugate. Therefore, let's actually take the parenthesis around that, and we take the conjugate, which is the square root of x plus h plus square root of x. We do this to both top and bottom. Now, if you look at the top, you'll be reminded of the formula, which is a plus b times a minus b equals to a squared minus b squared. So the top becomes square root of x plus h in parentheses square minus square root of x square, and the bottom remains the same. When you square those two terms on the top, square root and the square cancel each other. So we just have x plus h minus x. X and x cancel, we will have just h left on the top. We copy the bottom, and then you can see h and h cancel each other, and then you can simply substitute h equal to 0. And that will give you a square root of x, and then another square root of x. So square root of x and the square root of x, the final answer is 1 over 2 times the square root of x. So this is our first example using definition to compute the derivatives. Let's look at a few additional examples concerning the computation of derivatives. First, we remind us there are a number of formulas and differentiation rules. I will not go through the details. I expect everyone to remember those formulas. Those formulas would include simple-minded formulas such as fx plus gx derivative is simply equal to derivative of f plus derivative of g. A slightly more complicated one is the product rule, f times g derivative, which is equal to f prime g plus fg prime. We also have a slightly more complicated formula called the quotient rule. I will leave it to you to remember those. And we also have formulas concerning the power function, x to the nth power, and the trig functions. You need to memorize all those things, and keep in mind you can also create your own index card that you can bring to the exam, a 4x6 index card. So my here basically says you need to memorize this and prepare index card for those formulas. Let's talk about a more slightly more complicated rule called the chain rule. The chain rule basically concerns with a composition function. So let's denote the composition function to be f composed with gx. So fx here and then gx is substituted into f. That's the composition function. We are concerned with the derivative of this composition function. So we take the prime of that, which is the derivative. And the chain rule says, basically you take f prime x and then substitute gx into f prime. So this is the composition of f prime and gx. And then you have the times g prime x. So there is a multiplication here. Why do we want to call this chain rule? Where is the chain? Can you see that? So where is the chain here? Well, you will see this chain when you have compositions of more functions, more than just 2 functions, f and g. Suppose if you have 3 functions, f, g, and h composing each other. So f composes g and composes with hx here. Suppose you want to take its derivative. What's going to happen? Basically, you apply the chain rule 2 times, and you are going to get f prime composed with GHX as the first term. Take that and multiply, there's a multiplication here, multiply by G prime at HX, so G prime HX, and then multiply by H prime X. Therefore, you see a product of three different terms when you have three functions composed to each other. And you can imagine if you have four or more, you're going to have more and more products. And therefore, that is called the chain rule. There is the chain rule applied to the power rule, which I call generalized power rule, very useful here. So instead of x to n, we have gx to the nth power. And by the chain rule, it's going to be you take the n to the front, subtract the power by 1, that is like the usual power rule. And then you have the times g prime x at the end. An example. Suppose you want to take the derivative of square root of the following. Well, you write the square root in the form of 1/2 power, and then you apply the power rule, the usual power rule, which means you bring the 1/2 to the front, subtract the power by 1, in which case you will get a negative 1/2 here, and then don't forget the g prime, which is 2x minus 2 here. And after the cancellation of the 2 between top and the bottom, you eventually have the following result. Let's look at one more example, which will show you the chain. Suppose you have a composition of several signs, in this case, 3 different signs. And then finally, you also have a 2x. Really, this is the composition of 4 different functions. 2x is the first one, and sine, another sine, another sine. By the chain rule, you're going to have a cosine, which comes from derivative of the first sine, and then just put everything from here to here. That's the first factor, times the derivative of this part, which is cosine of sine 2x, then times cosine 2x, which comes from sine 2x, and then there's one more term. Which one is that? That would be derivative of 2x, which is 2. Now, I did not write the 2 here because I want to write the 2 in the front. That's why I left the space here. So we have 2 times the following. And that is the final answer. That's all for derivatives, and later I will talk about the implicit differentiation.